So we are dealing with the fifth problem in this series, and it is a very fantastic problem. Try to understand it every bit and part. The problem is stating the horizontal bottom of a wide vessel with an ideal fluid has a round orifice of radius r1 over which a round closed cylinder is mounted whose radius r2 is greater than r1. The clearance between the cylinder and the bottom of the vessel is very small. The fluid density is rho. Find the static pressure of the fluid in the clearance as a function of the time r from the axis of the orifice and the cylinder if the height of the fluid is equal to h. So we begin this problem by understanding the diagram which is given in the problem. So over here, if we consider this, so this is a fixed cylinder which we have. This is the fixed cylinder which we have. And the water is filled, or the fluid is filled to a certain height, and we have a small opening over here which is guarded by this small opening which we are considering as a small opening, and the opening is of a height t. Now the water will flow through this opening and then pour itself into this small orifice. So the first thing that we do is we consider a reference level. So we are marking this as the reference level in the problem. Now the opening 1 is at a height h above this reference level, and the 2 and 3 are on the same reference level. So we are marking h2 and h3 as 0 from this reference level, and h1 is at a height h from this reference level. The outside is at a atmospheric pressure P0. Over here let us consider pressure as P2, and over here where the opening is there in the orifice, we again consider atmospheric pressure. So P3 is also equal to atmospheric pressure, which is equal to P0. Now if we consider velocity of flow, so at the opening, that is the first surface, we consider the fluid is almost at rest, so V1 equals 0. The velocity of flow at 3 be V3, at 2 be marked as V2. So these are the necessary aspects which we have ascertained from the given diagram. Now the next thing that we do is we apply Bernoulli's expression between 1, 2 and 3. So I am writing one single equation and then we will break it into two equations. So let us begin by applying Bernoulli's equation from the data which we have gathered. So we are saying applying Bernoulli's equation. So Bernoulli's equation is stating P1 plus rho g h1 plus half rho v1 square equals P2 rho g h2 plus half rho v2 square, which is equal to P3 rho g h3 plus half rho v3 square. So over here P1 we are marking it as P0. It is at a height h, rho g h. The flow velocity is 0. At 2, P2 is P2. Reference level, at reference level 0. Half rho v2 square. At 3 it is equal to P0. h3 is equal to 0. Half rho v3 square. So from these three expressions that we have, we can equate either of them to obtain two equations. So we get P0 plus rho g h equals P2 plus half rho v2 square, and this will serve as equation number 1. And then we write P0 plus rho g h equals P0 plus half rho v3 square, and this will serve as equation 2. Over here if we eliminate P0, we will get two important aspects. Rho g h can also be written as half rho v3 square, or v3 can be written as root 2 gh. So we will use both of this later in the problem. We are marking it as 2. Now what we need to understand is the opening where the water is, or the liquid is pouring from the region 2 to the small orifice 3. So if we consider this, we are considering it using this diagram. So this is the cylindrical bore of radius r2 where an opening r1 is made, and the question is asking us to calculate the static pressure of the fluid in the clearance as a function of the distance r from the axis of the orifice. So at this distance r from the orifice, we need to calculate the variation of pressure. So we can consider that the fluid is pouring in from all directions. It is pouring in from all directions, and at this distance r, we are considering it to have a certain flow velocity. We are considering it to have a certain flow velocity, and eventually it is pouring into the orifice with velocity v3. So over here we apply continuity equation. So if we apply this continuity equation, then we can say that at any point a2 v2, at any point av, and at a3 v3 a3 v3. So over here we say that the fluid flow is taking place from all the sides. So over here we take circumference as 2 pi r2 having a width t. So the area will serve as 2 pi r2t, that is curved surface area, multiply by v2, and then we will equate it at any point which is at a distance r, 2 pi rt2 with a velocity v. Then again we at a3, so a3 it will be 2 pi r1 with velocity v3. So if we write the expressions, then we can write it as 2 pi r2 into t v2, which is equals to 2 pi r multiply by t having velocity v, which is equal to 2 pi r1 thickness t velocity v3. So this is the expression that we have from here. Now over here the velocity of flow at the same horizontal level can be determined, and we are marking this one as another important expression. We are marking it as 4. So we are asked to calculate pressure variation with distance r, that is P2 is to be evaluated from this expression. We need to evaluate P2. So to evaluate P2, we write from first equation, that is from equation 1. So we can write P2, which is equal to P in this problem. We need to find P0 plus rho GH minus half rho V2 square. So this is the expression that we have, and then we write it as P0 plus rho GH can be written as half rho V3 square minus half rho V2 square. So in the next we can write it as P0 plus half rho V3 square minus V2 square. Now if we solve this expression, then we can write over here V2 equals R1 V3 by R, and if we do the necessary substitution, so we can write it as P0 plus half, taken common we can write it as 1 minus R1 square by R square. So what we have done is we have taken this V3 velocity is out over here, and then we have substituted V3 square as root 2 GH, and then from here we get pressure variation with distance R as P0 plus rho GH 1 minus R1 square by R square. So this is how we solve this particular problem, which is problem number 1.321. So we need to understand this part very clearly. So RV2. So over here we are considering this one as RV2 as equal to R1 V3, and from here we obtain this expression that V2 equals R1 V3 by R, and then we substitute it over here to get the final answer which we have.